Section 6.1, Factors and x-intercepts. Recall the x-intercepts of a graph are where the graph crosses the x-axis. Since every point on the x-axis has a y component of 0, then these points will be in the form of a, 0. Every quadratic function is either going to have 2, 1, or 0 x-intercepts. Now, the x-intercepts can help us locate where the parabola turns. If the quadratic function has 2 x-intercepts, then the x-coordinate of the turning point of its graph will be right in between the x-intercepts. This is very helpful for very large graphs. If we know where the x-intercepts are, we can help track where the highest or lowest point is by first calculating what is directly in between the two x-intercepts. If the quadratic function has one x-intercept, then the x-intercept is the turning point of the parabola. We're going to find the x-intercepts for each of the following equations. First, let's take a look at y equals 3 over 14x squared minus 3 over 7x minus 15 over 2. We'll start off by typing our equation into Desmos. And here we can see the graph of our parabola here in red. Since they want us to find the x-intercepts, they want us to find where the graph crosses the x-axis. Well, taking a look, we can see 2 points highlighted for us, the points -5, 0, and 7, 0. The x-intercepts of our graph is -5 and 7. Notice here in this example, we had 2 x-intercepts. And if we take a look at the lowest point here, our lowest point where the parabola turns has an x value of 1. Well, in order to find the number directly in between -5 and 7, we can average the two x-intercepts. So -5 plus 7 over 2 would represent the number directly in between -5 and 7. And if we work that out, we get 1. And 1, we can see, is the x-coordinate of our turning point. Next, we're going to find the x-intercepts of y equals -x squared plus 6 minus 9. Going into Desmos, replacing our equation, and there's our graph in red of y equals -x squared plus 6x minus 9. Notice here along the graph, we only have one x-intercept. If we zoom in more, you can see that this x-intercept is the highest point of our parabola. It is where our parabola would turn. So our graph has only one x-intercept, and that x-intercept is 3. Now we're going to talk about a strategy for finding the x-intercepts. When we try to find x-intercepts, we are trying to make y equals 0. So if I look at the first equation, y equals x plus 3 times 2x minus 1, if I want to find the x-intercepts, I replace y with 0. But the problem is, in this scenario, I can't use the extraction of roots strategy that we learned in the previous section. There is a strategy and a principle we can use to help us solve this quadratic equation. To help us solve our resulting quadratic equation, we can use something called the zero factor principle. The zero factor principle states, if a times b equals 0, then a equals 0 or b equals 0. So if I take two numbers, multiply them together, and that product is 0, one of those two numbers has to be 0. So applying the zero factor principle to our equation here, that means the factor x plus 3 must equal 0, or the factor 2x minus 1 equals 0. So thanks to the zero factor principle, I was able to rewrite this quadratic equation into two smaller linear equations. Each one we can solve quickly. If we solve the one on the left, we get x equals -3. If we solve the one on the right, we get x equals 1/2. So here we have two x-intercepts, -3 and 1/2. Now we're going to find the x-intercepts of y equals 0.1 times 2x minus 3 times 3x plus 5. Because we're finding the x-intercepts, this means we want to make y 0. Now the 0.1 that we have out in front of our two factors is a non-zero number. We can divide both sides of our equation by a non-zero number. So we'll divide both sides of our equation by 0.1. 0 divided by 0.1 is 0. And on our right-hand side, the 0.1's cancel, leaving us with 2x minus 3 times 3x plus 5 on the right-hand side. Now we can use the zero factor principle and set each factor equal to 0. So we have 2x minus 3 equals 0, or 3x plus 5 equals 0. If we solve each equation, we get x equals 3/2, or x equals -5/3. So the x-intercepts of y equals 0.1 times 2x minus 3 times 3x plus 5 is 3/2 and -5/3. If we know the x-intercepts of a quadratic equation, we can form a quadratic function to help us model that graph. If f of x is a quadratic function with x-intercepts of r1 and r2 and a leading coefficient of a, then f of x equals a times x minus r sub 1 times x minus r sub 2. Now this form f of x equals a times x minus r1 times x minus r2 is referred to as the factored form of the quadratic function. If we take a look back at the previous examples, those were all in factored form, making it much easier to solve for x. So now we'll turn our attention to example 3, where we're going to write the factored form of the function based off the given information. The function f of x graphed is quadratic with a leading coefficient of 1. With the phrase leading coefficient of 1, I know right away a is equal to 1. Now I have to figure out what r1 and r2 are. Then I can throw everything into the factored form that we saw above. Well, if I take a look at the graph, r1 and r2 represent the x-intercept. Well, I can see that the x-intercepts occur at -1 and -2. It does not matter which x-intercept you make r1, which x-intercept you make r2. We'll make -1 r1 and -2 r2. If you switch, you'll get the same answer, maybe just written slightly differently. Now that we know a, r1, and r2, we can write our function. F of x equals 1 times x minus -1 times x minus -2. Then we can do a little bit of cleanup. Anything times 1 is itself, so we don't have to write the 1 that we have all the way in the front. And then we can clean up the signs in each factor. Negative negative is a positive, so x minus negative 1 we can rewrite as x plus 1. X minus negative 2 we can rewrite as x plus 2. And now we have our function. Now we're going to take a look at a problem that can quickly be solved when we have a quadratic equation. Paul wants to build a fence for his farm to enclose a carrot patch. He wants to put the fence against a wall that is already on the farm and only has 50 feet of fencing to make a 3-sided enclosure. With this information, we're going to figure out 2 things. First, what are the dimensions of the enclosure that has the greatest area? And our second question, if Paul wants to create an enclosure with an area of 200 square feet, what are the possible dimensions of that enclosure? To help us answer both of these questions, we want to start off by drawing a picture to help us organize the information, since this is geometry based, and then from the picture, we can start forming equations. Now, we know we have a wall on the farm, which I'm going to resemble with this blue line. The other 3 sides are going to be our fencing, which I'm going to put in purple. Now, just pretend that I did draw a really good rectangular fence. Your picture does not have to be a work of art, but something to help us get the idea of our situation. Now, if we think about what we want to figure out at the end of the day, well, we want to figure out the maximum area, or the area is 200 feet. What are the dimensions that cause the area to be 200 feet? So we're going to need an area formula. Specifically, how do we find the area of a rectangle? The area of a rectangle is equal to its length times width. I'm going to make the length the side parallel to the wall, and the width is going to be the length of the sides perpendicular to the wall. The problem is I still have too many variables. I have length and I have width. The only piece of information I haven't used yet is that I have 50 feet of fencing. Well, how does 50 feet of fencing help me relate to my variables? I'm taking the 50 feet of fencing and I'm using it for 2 sides that are measured W plus 1 side with a measure of L. So 50 equals 2W plus L. Now we're going to solve for one of the variables in our 50 equals 2W plus L. And we're going to plug that into the area equation that we have now. This way, we can rewrite area as an equation with 2 unknown variables and make it into a function with only 1 variable. Well, to solve for one of the variables in the 50 equals 2W plus L, it doesn't really matter which one you solve for, but the easiest variable to solve for here is L. This is because in order to solve for L, all we would have to do is subtract 2W from both sides. Whereas if I choose to solve for W, I would have to subtract L, then divide by 2. So we get 50 minus 2W equals L. Now we're going to take the 50 minus 2W, plug it into our area equation, and we get that area equals W times 50 minus 2W. And we get A equals W times 50 minus 2W. Notice how our right-hand side only has W. So we wrote our area as a function of W. So we can say A of W equals W times 50 minus 2W. Now, what are the dimensions of the enclosure that has the greatest area? Now we can go to Desmos and type in our area function. Now, immediately, I don't see anything on the graph. If I use what we did in the previous slide, I know one of my x-intercepts should be 0, because if I set this W equal to 0, I'll get 0. Also, if I set the 50 minus 2W to 0, I would get that W equals 25. So I should zoom out until I see x equals 25. And there we can see our x-intercepts. Now, how does this help me figure out where we have the greatest area? The highest point of our parabola or the lowest point of our parabola will always be in between the x-intercepts. Since I know my x-intercept is 0 and my other is 25, I know now my highest or lowest point will be between 0 and 25. And now seeing how we trace the graph, we can see that it looks like both ends are getting closer and closer as we get higher and higher. So I'm just going to keep moving my graph upwards. And we can see now there's our highest point. Our question is, what is the dimensions of the enclosure that's the greatest area? Recall that the y component of our points will represent area. The greatest area for any enclosure I can make is 312.5 square feet. Well, the first component will tell me the width of the enclosure. So my width must be 12.5 because that is the number I would have to plug into my area function in order to get the highest possible area. But I also need to know my length. In the blue box, we found the relation that L equals 50 minus 2W. So now that I know the width is 12.5, I can use that relation to solve for L. So here, L equals 50 minus 2 times 12.5. And if we work out the arithmetic, we get that L is 25 feet. So what are the dimensions of the enclosure that has the greatest area? Well, the width, the length of the side perpendicular to the wall would have to be 12.5 feet, while the length of the side parallel to the wall would be 25 feet. Next, we want to know what are the possible dimensions of an enclosure that has an area of 200 feet squared. Because we know our maximum area is 312.5 square feet, it is possible to make an enclosure with 200 square feet of area. To help us solve, going into Desmos, we're going to type in y equals 200. Now, nothing immediately shows up, but if I scroll down, we can see that the y equals 200 is in green. And remember, Desmos does highlight points of intersection for us. So we can see 2 scenarios where my area can be 200. Scenario 1, the width is 5, or scenario 2, the width is 20. But remember, they want the dimension, so that's length and width. While still using the length equals 50 minus 2W, in the first scenario, our length would equal 50 minus 2 times 5, which is 40, and both units are feet. In scenario 2, the length is 50 minus 2 times 20, which is 10. And again, the units for both would be feet. And that's the 2 ways we can make an enclosure with an area of 200 square feet. Either W is going to equal 5 feet while the length is 40 feet, or W is going to be 20 feet while L is going to be 10 feet.